So, hello everyone, very good evening. I think I'm audible. Very good evening to one and all. Welcome to our 30-day masterclass on advanced VLSI design and verification. Today is the 23rd day of our masterclass. So, I think I shared all the attendance link for the 22-21. So, please try to fill the attendance. So, and then very good evening to one and all. Thank you for your presence. So let's wait for a few minutes. Today we are gonna see code implementation of APB protocol. So last class we seen how the design code, how the what is the spec of the APB protocol, what are the signals. So and then how the data transfer happens in the APB protocol. So how many cycles it's need for to make one transfer. So this kind of things we already seen in the last class. Today we are gonna see the coding part of the APB protocol. And all. So I think it's clear now. Can anyone respond in chat box? Is my voice is clear? So I'm facing some network issue. So very good evening, Sri Krishna. Is my voice is clear? Can anyone respond in chat box? I think I'm facing some network issue. Is everything fine from my side? Can just put yes in chat box. Then only I can move further. Yeah, okay. Thank you for response, Bharatra Singh. Thank you for your daily presence. Directly we are gonna see the coding part of the APB protocol. So before going to that, just recall some technical terms of some technical things of our APB protocol. So main thing is APB protocol is a on-chip protocol. It need two clock cycle to make one transfer. The based around the P enable signal. So P is a prefix of APB protocol. Why? Because of APB protocols comes under the AMBA protocols. It having the three types of protocols like APB, AXI, AHP. So APB is a low speed, less performance, and then low bandwidth protocol. So it is mostly useful for interface peripheral devices with the chip, and also it is a power consumption. But compared to the AHP, AXI or high speed protocol, they are using high bandwidth, high clock frequency. They are mostly used for high speed protocol, high speed communications like memory to CPU, processor core to CPU memory communications like RAM memory to CPU core, or else other like a DMA with the CPU core. So to make between the communications, the high speed protocols like AHP, AXI are used. So we are gonna see the APB protocol. It is a low performance, low speed protocol. So it is mostly used for interface the peripheral device. Okay, this APB protocol just briefly. So and then the main is it having some signals like a P clock, P reset, it is an ACTE reset, and then P address, P write data, P write, and then P enable, P slave error, P select. So these are the basic signals of APB protocol. By using this is a main IO signals of APB protocol. Okay, and then it having it take two clock cycles, one for setup and then another one for access. So there are three states in the APB protocol like idle, setup, access. Okay. So very good evening to one and all. Thank you for your presence. So Naveen, very good evening. So and then thank you for joining. So we'll start now. Okay. So and then I will just show you the FSM for the APB protocol. Why? Because of FSM, finite state machine is very important while writing the design code. Okay. So directly I'm going to I will show you the basic signals of the APB protocol. P clock, P reset, and P address, P cell. So P cell is nothing but this is a signal to select the slave, which slave the master wants to communicate. So for the selection purpose, we can use this P cell X, this signal. okay. And then PR data, PW data. So this is a PW is a main signal. It is a P write data. It is a raw signal where the protocol gonna send the data from master to slave, okay. And then PR data is a slave response signal. This is a slave output. It is an act as a input for master. So and then P write, if it is high means the master can write into or can send the data into slave. If the P write is low means the master only receives the data from the slave, okay. Slave can send, master must have to receive the data, while P write is 0. You can see here on high is this indicates APB write access, when low it is an read access, okay. These are basic signals of APB protocol. So and then there is a black diagram of APB bridge. So this is a slave interface. This is a combination of master slave interface. This is a main thing of APB FSM, finite state machines. Totally it having the three states: idle, setup, access, okay. So ideal means how we can define the ideal state means if the P cell and also P enable are both the 0 means we can say that the bus protocol are in the idle state. So how we can say means P cell equal to 0. It means we don't know the protocol don't know the slave, which slave the master have to communicate, we don't know that. So that we can say that this is an idle state. And also P enable is 0. So if the P enable is high means then only master can make the transfer. So if the P enable is 0 means there is no process won't happen. So we can say that it is an idle state. If the P cell and then P enable signal both are low means it means 0 means we can say that it is an ideal state, okay. So and then setup state. So how we can define a setup state means if the P cell x is 1, P cell x equal to 1 and then P enable equal to 0, it means selection line having 1. So we know the master know the slave device to communicate with that, but the master is not ready. So it is known as setup state. So in that time all the remaining signals are sampled, like a PR data, PW data, and then P write, and then remaining all the P slave error. So remaining all the signals are sampled in the setup state. So in the access state the main actual data transfer will happen. So if both P cell and then P enables are high means a master can send or receive the data from So the master can make the transfer in the access state, okay. So sir, please X. So X. So in the X in the P cell X, it's a APB select signal. Select the slave. This axis refers to slave address. If it is for example, assume like I am having the 5 slaves. So the name of slave is slave 1, slave 2, slave 3, slave 4, slave 5. So if you master want to communicate with the slave 2 means we can say like we can write the code logic like a P cell 2. It means the slave want to communicate with the slave 2, okay. And then the master wants to communicate with the slave 2. If the P cell is equal to P cell instead of X it having 3 means P cell 3 means the master can communicate with the slave 3. So this is the thing of the APB like a slave address, okay. How many bits? So for to define the bits we can see in the I think it is the name. So it is a single bit. It is the signal from the secondary decoder within the peripheral bus bridge, but you need to reach peripheral bus slave X. The signal indicates a. So it's like our wish. It is our if you make like a logic 3 down to 0 means it is a 4-bit signal. So if you are using the 5 signal, so 5 slave device means you need 3-bit, okay, at least 3-bit of signal. So 3-bit of vector, then only you can define the 5. If you are using the 10 slave means you need the 4-bit, okay. It is fully based on our wish. So based on the slave count we can increase the slave address, okay. So the slave address fully based on our wish. we can assign as much we want for the slave address vector. So and then we'll move into coding part. So this is a basic information about APB protocol, FSM. So and then firstly this is a code. So I just close this. So firstly so today I'm going to make the one kind of single master single slave. So there is a slave, the slave will do the read or write operation. So it's like a memory. So it is assume like a slave device is as a memory. We can write into memory, read from the memory. So we'll see the memory slave code for the APB protocol. Okay, so you can see here I defined three parameters like ideal 0, setup 1, access 3. So this is my three states I defined here. We can also use parameter. So I am using some different method to define. Okay, so and then this is my module APB design code APB underscore memory. So here I am assume like a APB slave device is like a memory. Okay, memory we can write into memory, we can write from the memory. Okay, and then you can see here p cell equal to 1. This is my first slave, and then clock I am only having the only one slave. So that's why I am telling like this, like if you are using more number of signals means you have to give the vector form, input 3 down to 0, input 2 down to 0 for the p cell. Okay, so here I'm having signals of p write, p enable, p address. So address is a 32-bit signal. We know that write data also 32-bit signal, p data is also 32-bit signal, and then p read is single bit, and then p slaver is also single bit. Okay, so these are the main input output signals of my APB okay, APB slave. And then here is a I'm having the to make the state transition. I'm creating the two registers like a state, the next state, and then for the delay purpose I'm creating another internal signal like a delay. It is a 2-bit signal. So here I'm creating the memory. So memory is 31 down to 0. Memory is this is my array name like a mem, and then 2 power depth minus 1 down to 0. It means I'm already defined like a depth equal to 5. 5 means 2 power 5 is a 32 minus 1. So it means it having the 32 memory location. Each and every memory location we can store 32 bit of data. So this is a memory creation of my APB slave. Okay, so and then here you can see here in the initially I am staying in my ideal state. So tick ideal, it means I am staying in my ideal state. So why I am using tick, this symbol you can see here, this like this symbol is refers to tick. It is refers to tick. Why? Because of I am using like a defined functionalities of SystemVerilog. So it is like it is also like a parameters. So but if you are using the define means you have to follow this tick symbol. If you are not using defined functionalities means you can use the parameter like a parameter ideal 0, parameter setup 1, parameter access 3, access 2. So this is how we can use in the our code. Okay, so in the initial stage of simulation I am staying in the ideal state. Okay, so and then if the I am using the APB protocol is active low reset, it means if the reset is low means it is in the reset condition. If reset is high means so it will do execute of what you are given, what you are written in the code. Okay, it is an active low reset. So if reset is actually if it is true means I am staying in the idle state, and that time I am assigning my memory. I have one memory. I am assigning the 32 bit of f inside my memory. Why? In the all the 32 memory locations, I am assigning the 32 bit of f in my all the 32 memory location in my memory. Why? Because of I'm staying in the idle state. So in the idle state there is no data transfer will happen. So I'm staying. I'm like setting like these conditions. In my reset condition, in the ideal state, the APB protocol, the slave device must be in the reset condition. The reset condition is nothing but I am assigning the 32 bit of f in my memory. Okay, if it is not in recent condition means I will move into next state. Okay, state transition. So here you can see here I am using one always block. The event triggering of always block is state P cell P enable. So P based on the P cell P enable signal only I am changing my states. Okay, I'm changing my states. So you can see here in the idle state means P cell also the P cell and then P enable must be 0. In the setup state P cell equal to 1, P enable equal to 0. In the access state P cell also must be 1, P enable also must be 1. Then only we can make transfer in the access state. So same like here, based on these two signals this always block is executed. Okay, that I am using the case here. If a case state in the idle state means I'm just defining the state. What is in the idle state? What is in the setup state? So what is happening in the access state? Okay, in the idle state I already said no. All the signals like a P slave error, P ready, PR data are 0. Okay, so and then if the P cell is 1 means I can move into setup state. If the P cell is low means you can see here if the P cell is high. Why? Because of it is a single bit signal. If it is high means it can move into setup state. Or else if I am using the 2 or more slave device means here there is a chance to get the give the some conditions like a P cell equal to 3, P cell equal to 3, if P cell equal to 3. So we can give the address for the P cell. So but here I am using only one slave device. That's why I am directly checking. If the P cell is high means I can move into setup state, or else I am staying in the idle state only. So in the setup state, this is my setup state. Okay, here I am going to checking my P slave error. So this is a one signal P slave error. It indicates the error messages to master. If the slave device feels like anything error means it can respond to master by using this P slave error signal, PSLVRR. By using this signal it can respond to the slave. Okay, so and then if the P enable, so you can see here if the P enable is high, based on the delay I'm just giving my P ready equal to high. So and then I'm checking one conditions. If my address is more than depth, okay, if my address is more than memory location depth means I'm just assert P slave error equal to 1. Why? Because of the depth is more than address, so you can't write the unknown addresses. So I'm just displaying my error messages by using the slave error signal. So memory address more than limits. This is my error message. So again this is also my second error message, invalid data if in the PW line. Why? Because of PW data. PW data is my read or write signal. Sorry, this is my write data. If the write data having the X or Z, like a X or Z, high impedance means I unknown, or if the PW data having some unknown or high impedance value means I can say that that data having some unknown invalid values, so it is some kind of error. So and then P write equal to, so if you can see here P write equal to low, it means I can read from the data. So I can read from the if a P write equal to 1 means I can write into slave. If my P write equal to low means I can read from the slave. So here it's happening the reading from the slave. Okay, so and then you can see here it happening the reading from the slave. So I'm just assigning directly PR data is my slave output signal. I'm just assigning the whatever I'm storing in the memory based on the address, I'm just sending to PR data. So in the and then if the P enable, you can see here after this completion of the after this I am just moving into next state, it is a next state equal to access state. So in the access state, if the p rate equal to high, there is no slave error, means I can write into slave. Okay, so how we can write into slave means, slave is a memory. So this is my PW data. PW data is nothing but my write data, master is sending to the slave. So I'm just assigning to my memory. So here memory is act as a slave. So I'm just assigning to my memory based on the address, p address. Okay, so and then if the p cell is high, again high means, so if the p cell is low means I can move into idle state, or else I can move into setup state. So this is a basic example, basic code for APB design code. So attendance link, so I will share the link now. Just a minute, give me a minute. I will share the 23rd attendance link. So I will share the attendance link now. Just a minute. So you can fill the attendance in chat box. I will share now. So I share the attendance link. Just to fill the attendance link for 23rd live session. So again I will pin in my top. So I share the attendance link for the today's session. Just fill the attendance link. So and then today till now we are seeing only design code. So we are gonna see the test bench architecture, SystemVerilog test bench architecture for APB protocol. Okay. So here we know that test bench architecture is having some class like a transaction class, driver class, generator class, input monitor, output monitor, scoreboard, and then environment, and then test interface, and then design code. So okay, so it is like a DUT we are having, and then interface we are having, and then test bench we are having. So from the test bench, it having the class is a dynamic in nature. It will do randomization, and then it will transfer into DUT by using the interface. Okay, so interface acts like a converter from pin level to packet level to pin level data. Okay, so I think you guys are remember that the AP test bench architecture for SystemVerilog. I hope it's clear for you. Just I am showing the code of the APB, test bench architecture. Before going to that, I want to share one thing. So if you want to convert this masterclass into 1 month of internship, you can convert by using you can convert into 1 month internship. So you will get the benefits like all 30 days recording session, all 30 days PPTs. You can also this kind of we are providing this kind of source codes. You can download also. It is very useful for you. You can refer as for your future, and also you will get the internship certificate from IETE. So it is an valid certificate. So all these benefits you will get at just discounted fee of 999 only. So by using the registration link, the registration card already in the chat box. You can see you can get the link in chat box, and also in the description of a live video session. You can buy the internship program, so you will get these benefits like a source code download, and then PPTs, and then we are providing weekly live sessions after the 1 month for your doubt clearing, and also we are giving some mock interviews kind of thing. So if you guys are interested, you can convert into masterclass into 1 month into internship. You can use the registration link in the description and also in the chat box. So firstly I will show you this is my design code. Okay, this is my APB APB underscore mem. This is my design code module. Again, I'm going into transaction. So we know that transaction it having the all the signals, okay, all the signals. So transaction is one class, it having the all the signals, okay. So here you can see here it having all the signals with the rand keyword. So but with the rand keyword only we can do randomization. So why we are using this SystemVerilog architecture means, so without this means we can use classic classic test bench to verify the design code, but it will take more time to cover the all the test scenarios. Why? Because of it having a 32 bit of width, 32 bit of width, like address width, data width, and then output RPR data is also 32 bit width. So we can't we can't test all the scenarios. It will take more time to write the classical test bench. But here we are doing randomizations, we having the constraint support, we having the coverage support, we have assertion support. By using this we can control the randomizations, we can check the randomizations, we can check the coverages. So this is the main advantage of the SystemVerilog architecture. This is the main thing of SystemVerilog languages is was introduced. Okay. So this is the main signals of our protocol. There is my PRD, PR data, its output signal is a slave error. It is also slave output signal. So these signals are comes under the master signal. This is my slave output signals. Okay. So and then how to write this big length code. So how to write the big length code means, so if you are well trained, if you are well know SystemVerilog language, if you are very good in protocol, like what are the main things, if you are well experienced means you can write your own. But as of now you can't. If you are fresher, if you are new to Verilog, SystemVerilog, or new to VLSI field means, at least you have to spend at least 5 years, then only you can make own functional correct synthesizable SystemVerilog code, synthesizable design code. At least you have to spend 5 years. Okay. So but you can learn by using the reference codes, like you can get the reference code from the there are a lot of open source like a RISC-V. So many companies are using the RISC-V architecture. They are providing some open source code for AMBA protocols. You can refer that, you can get the codes in GitHub, so you can understand, you can refer that. Then only you can slowly you can write your own code, you can develop your coding skill in the SystemVerilog. The main thing is you have to test, you have to practice every day, then only you can write your code like this very big code. So compare this very simple, only one slave device, one SystemVerilog test bench architecture. If in the industry side we having some multiple slaves, okay, there are 10 to 15 number of slaves. So there is one master, so slave address. So and then for the slave selection we have to use T code, and then we have to make communication between the AHP to APB. So AHP having lot of signals, and then AHP protocol also lot of signals. It's an high speed protocol. So there is a clash between the high speed clock, low speed clock. If you are working with two clock domains with different clock with different clock frequency means, you will get a lot of issues. Why? Because of there is a clock domain, there is a mismatching of clock. Why? Because of APB need 2 clock cycles for one to make one transfer, but in the AHP it take only 1 clock cycle to make one transfer. So if it is like there is a speed difference, so APB will send the data very slowly, but AHP always looking for getting data very fastly. So this kind of issues may happen while writing the design code, and then this very hard to verify that. So that this kind of scenarios you have to avoid, you want to avoid means, whether you have to practice every day, and then you have to learn all the techniques. There are a lot of techniques for clock domain crashing synchronizer. So making synchronizers you can use a lot of techniques. One of the best technique is you can use the FIFO buffer. Okay, this is my one of the best techniques. Already we seen in our masterclass how we can use the FIFO buffer for different clock domains, different baud rates in UART. It is very important. And then you can use a lot of techniques like a toggle synchronizer, clock synchronizer. So there are a lot of techniques there. So how you can learn this technique means by experimenting, by writing, by working with the code only. You can improve your coding skill. Okay. So thank you guys. I think it's clear for you, Vijay Kumar, Naveen Rathe. So very good evening, Vijay Kumar. So thank you for response, Bharat Singh. So and then this is my transaction. So here I am doing some constraints operation, and then here I'm doing some pre-randomized post-randomized operations to count my randomization, to how many randomization. If now I'm doing only randomizations, so now I'm counting the how many randomizations are happened, so how many post synthesize are happened. Okay, so Hindi, and I'm having the some function here, printf. It will display the all the signals values. Okay, it will display the all the signals value. You can see here it will display the p write, p reset, p cell, p w data, p address. Okay, so and then it is input for the DUT. So and then output from DUT is p data, p slave error. Okay, the slave is a only one design code. The inputs are p the slave device some need inputs. That inputs are given by test bench, and also slave will give the output to test bench. Okay, the main thing is I'm going to compare that. So I have one reference model code, reference model. If I want to check that whether the output of slave is equal to reference model. If it is equal means, so it is working correctly. We can just verify that by using this only. Okay, so and then here I'm doing the self bit comparison of my output signals from DUT with my transaction. Okay, so you can see here this is my function name, transaction name. This is I'm instantiating class in my parameter of function. So this is this keyword is refers to this current class. Okay, I'm assigning the so here this is a trans dot p ready. So this is a p ready signal. It's come from outside of the class. I'm just receiving that signal. I'm assigning to my current class. Okay, this is the main thing of this keyword. So if it is 2 means return 0 or else return 1. So and then if it is this condition is fails means return 0. So this is my logic of function. So and then I'm going to show you the generator code. So the generator code, what it will do means it will do randomization. Okay, so you can see here. So I want to send the data from generator to mailbox. So sorry, generator to driver. So for that I can use the mailbox here. We know the mailbox interprocess communication we already seen in the previous classes. Mailbox, it can send the data from one class to another class. Okay, so I'm creating one mailbox here, generated to driver. So and then I'm creating event triggering driver run, and then I'm making transaction handle as a 2. Trans is my first handle for my transaction class, and then trans to driver is my second handle for my transaction class. So and then I'm assigning this new function will receive the handle parameters from the outside of the class. Then I'm assigning into my current class. So and then here I am doing this is my run. This is my main task, run task. Here you can see here I am doing the randomization. Here I am doing the randomization. So here I am doing randomization, trans.randomize. So and then this is my main start task in my generator class. So what I am doing means I am just counting my packet ID. Okay, packet ID, feature ID. So and then this is my basic. You can see here I am just here putting into I'm just doing here. I'm just whatever I'm randomized data I'm just putting into my mailbox, transaction to driver. This is my mailbox. Okay, So I'm just putting into my so whatever data in here it having like a trans to driver, I'm just putting into my mailbox of generated to driver. This is my mailbox name, generated to driver. So if the event I'm waiting for the event, if it is triggered means after 2 nanosecond, I am just I'm just following my for loop. It will do the test case count. Okay, so and then I will move into my driver class. So driver will send the data to the DUT. Okay, how it will do means, so by using the virtual interface it can do the data transmitting between the classes, like a classes from classes to DUT. It's a driver class to DUT. So driver is implemented using the different operating states of APB protocol. The different states are implemented as a task. The driver task switches between the different status according to the P-ready signal and number of transfer that needs to be done. So main thing is here I am just saying the what is the idle state values, setup state values, access state values. You can see here this is my idle start. I am just saying, you can see here virtual APB underscore interface dot drv, and then this is my virtual interface name. So I'm having one block like interface end interface. This is my interface block. So what it will do means, it will make communication between the DUT and test bench. It's like a transmitter receiver kind of thing between the two blocks. Okay, so if the P enable should high 1 clock cycle after, so this is my basic information about P enable. So here also it having the IO signals. The main thing is the test bench output signal is input for DUT. The DUT output signal is input for test bench, like a PR data, P slaver, that these are input for test bench, and like a P write data, and then P write, and then P address, P slave X. These all data are randomized in the test bench. This is act as a input for DUT. Okay, I think it's clear for you. So by using the clocking block, we can make the direction output direction, input direction among the design code and then test bench code. So that's all I'm doing here. So and then due to some time constraints, I'm going fast, so I pick it off. It having the n number of lines. If you want, it is a very huge task to explain one by one line. Okay, so and then there is a interface. In the driver, I am making a virtual interface. By using the virtual keyword, we can make the communication between the class to module. Why? Because of class is dynamic in nature. Dynamic in nature, but module is a static in nature. By using the virtual keyword only, you can make communication between them, dynamic to static. So dynamic to static, like a class to module. Okay, here this is my new function. I'm assigning the some parameters. I will what I'm getting from the outside of the class, I'm just assigning to my current class. So in this my ideal task, so PCL equal to 0, PNB also 0. In the setup state, PCL equal in this setup state, PCL equal to 1, and then P enable equal to 0. Remaining all the data are sampled. So here in the access state, PCL equal to 1, P enable is also 1. So you can see here, this is my virtual interface name, this is my clocking block name, this is my signal name. So if you seen in the interface, it having some which I will show you. Here is a scoreboard drv underscore cb. The interface it having some clocking block here. You can see here clocking block here. And then outputs are P write, P w data, P address, P enable, P reset, P cell1. These are the output of test bench, and then input is P ready only. Okay. So same thing. So in the again in the driver, so I'm just the main thing of interface is to give the directions of the both design code and then test bench code. Okay. So in the driver again I'm doing some driver operation. okay, and then it will send the data into the DUT. Again, it is my main start function, sorry, start task. Again, here I'm calling the ideal task. Uh, get my data from what I am getting from the mailbox. This is my get method for the mailbox. This mailbox name generated driver. I'm get the data in the mailbox by using this get method, and then I'm calling the drive task here. This is my drive task. It will drive the signals to the DUT. And then again after this task, I'm just event triggering my event triggering like a drive done. So I'm just triggering my event triggering. So this is my driver class, and then I'm showing the again input monitor. So the input monitor will make the transaction packet from the sampled APB signal, like it will master to send. So it is master to slave. So the driver will send the data to my input monitor will send the data to DUT. Okay, so here I'm creating the virtual interface here again input to reference module. So why I am using the reference module? So you can see here IMMON, input monitor to reference module. So here I am sending the data from input monitor to reference module. Why I am sending to reference module means, so I need to compare some values, right? So I need to compare DUT output with something so something like a reference module. So the reference module and also DUT output must be same, then only I can say that it's working correctly. So to verify that, I want to make some reference module same. It will works like a DUT only. So DUT output isn't test bench, like a reference model output must be same. So that we have to again write the DUT logic in our test bench. So again here I'm also creating my mailbox, and then I'm also creating my depth. Okay, I'm also creating memory, like you can see RAM memory, and also here I'm getting some ideal access, ideal state process, and then is my setup state process, and then this is my access state process. Here I'm doing some same logic what I did in the design code. Okay, in the start menu I'm just getting my data. I'm just getting my data from the mailbox, and then I'm calling the task generator operator, and then operation, and then I'm just putting whatever after the reference module I'm just putting into my mailbox. The mailbox name is trans to SP. It means transaction to scoreboard. Okay, in this scoreboard I'm just comparing that whether I'm receiving correctly or not. So this is my scoreboard. Here I'm getting the data from reference module and then output module. Okay, output module, reference module. So I want to compare that output module is data has come from DUT, reference module is having some reference data. So I just need to compare the both output module data with reference module. So for that I am calling one compare function, which is this is my function name compare, which is inside my transaction class. This is my transaction class. Here I am doing the comparison between the PR data or trans PR data with the current model BPR data. Okay, I'm just comparing the output signals. Okay, so it will compare the output signal, both output signals from the DUT and design code. Okay, in the scoreboard I'm just calling the compare function. Okay, you can see here if the transfer from the from output monitor dot compare trans from the reference model. So it is a compare functions. It will compare the both modules, both like a mailbox data. If both are matching means the test case is passed, and then it will print the packet ID, and then it will move into packet. It will increase the packet ID. It will move for another randomization. If it is failed means it will report the fail message. Test case is failed. Okay, like that. So this is how the scoreboard will compare the data. So and then this is my start menu for the trans from reference module. Again, this is my main function. We get to print the report, how many test cases are passed, how many test cases are failed. Okay, this is my total report. So and then this is my main thing of scoreboard. Again, coming to the environment, I'm just instantiating the, I'm just making the handle for the all the classes, and also I'm passing my parameters, and then I'm calling my the all the new functions inside my the function new function in the environment class. Again, in my build task, I'm just calling my all the new functions inside my the classes. Again, in the environment, I'm just start, I have one main start task here. In the task, I'm calling the classes task, like a transaction class task, driver start task, and then generated start. So this all driver dot start, it is a calling of start task inside my generator class. So drv dot start, it is nothing but I'm calling the start task which is inside my driver class. Okay, so I'm calling the all the tasks from inside my remaining like a classes like a driver, generator, scoreboard. Okay, inside my environment class. So after this in the test, again I'm calling the again in the here it having some write transaction, it extends, so write transaction, it's my own class. Here I am doing the, I can switch off on the randomization mode, and this is my main test class. Here I'm making handle for environment class. By using the environment class, I can use the environment class properties and methods. So again, here you can see, here I am giving the test cases, how many test cases. So I'm giving the 800 test cases for randomization. Again, I'm calling the build task and then run task, which is inside my environment class. Okay, and then again in the top, this is my top module. So before going to that, I will show you my packages, APB packages. So I've just created a file called SVH. It is a header file of SystemVerilog. We can include all the Verilog SystemVerilog files you have, what you want to included. Okay, we can include like this. Is my package file. So in the top file, so db underscore top.sv, it's my top file. Here I am doing instantiation of my design code and also interface. Okay, by using interface only I can access the testbench classes properties. So and then I'm creating the class over here. Again, I'm by using the, you can see here test. So test is my test class, it having the handle name for the environment. So by using the test handle, I can access the environment handle. By using the environment handle, I can access the remaining class and properties and methods. Okay, so in the test task, in this tb underscore top, so I'm just by using the handle, I'm just calling my new function, and also I'm calling my run underscore test. So run underscore test will it will automatically execute the remaining tasks. Okay, so this is my basic flow of APB protocol verification. So it is like a framework, so I think it's a little bit hard to understand with the first time, so but it will take more time to understand. So if you got this code, means you can easily understand, so you can easily understand how you can improve your Verilog SystemVerilog skills. So and then I'm going to run this code. So for that, I'm just open my terminal. So and then I'm directly just a minute, directly write vsim. So it will open the CostaSim tool inside my current working directory, inside my current working folder, with the single keyword like a vsim. So again I will do a search. I'm doing run.2 here to run the APB protocol code. it will take some time to run the simulation. Why? Because of there are a lot of lines of code. We are creating the memory. So I will show you that how the memory list looks like in the QuestaSim. Okay. So this is my output report, what you are seeing currently. So and then, so before going to the see output, I will show you the memory list. You can see here, just a minute. Okay, you can see here memory list. I'll just okay, this is my in the view. Go to in the view, you can see the memory list. So from your this main window of your QuestaSim, here you have to click here memory list. Here you have to choose memory list. You can see the memory list of your code, your design code. You can see here just a minute. You can see here mem. So tb and underscore t top and dut mem. So this is my memory of this is my memory which is in my design code. So I already said no, I created one memory, that name is mem. So the range is 31 down to 0, and then depth is 32, width is also 32. So I just created the memory of 32-bit memory location. So 32 memory location. In the each memory location I can store 32-bit of data. This is how we can create the memories in the design code. You can also see in the QuestaSim tool. So memory list. Okay. So and then this is my report. So you can see my final report is there are total number of test cases 116, pass cases 116, there is no fail case. So 0% of fail class. Why? Because of I return the coverage, assertion, and then constraints. Okay. And then feature these I'm having the 5 feature IDs. Feature ID 1, 2, 3, 4. Each and every feature ID it will do some randomization process. Okay. 2, 6, 8 of 1, 2, 9. These are my total test cases are done by the randomization by that tool. So how you can check means, so if you scroll means you can see the reports. For example, okay, this is my, you can see here inside that you can see here packet ID. Packet ID is here 773, feature is here 4, input to DUT. This is my display statements which is written in my transaction class. These are my values: p write 0, p reset 1, p is equal to 1. This is my address. P write data is my, this is my p write data. Then this is my p write p address. This is my p write address randomized value. Then what are the data I got from? This is my data I got from the PR data, and then there is no p slave error. So and then received from the output monitor in scoreboard. So packet 773, feature ID 3, input monitor. So I'm just comparing over here, and then you can see here size equals 0, packet ID 773 is passed. So why? Because of I'm just checking the output. If it is both are matching means it is displaying test case is passed. Okay, and then you can check the remaining all the test cases by using like this. So this is how we can make the SystemVerilog test bench architecture for your design code. So this is how the industry people are also working together. And also in the here in the coverage, go to the cover groups. In the go to views, and in the coverage go to cover groups. You will see the coverage reports also. You can see here these my coverages I already written. So I will share the coverage things in the upcoming classes. Only we have only seen like a assertion only. So in the future master class we can see the coverage also. Why? Because of coverage is also a very important topic. It is a very big topic also. So this is my coverage reports, coverages. So you can see here p write data, all the randomized are covered. Okay, all the form of constraint which is given by me is covered. Okay. This is how we can write the SystemVerilog code for APB protocol design code, and then I will show you the final report over here. There are total number of test cases 800, total number of fast cases 800. There is no fail case. Okay, there is no fail rate. This is how we can write the SystemVerilog code for verification. Okay, I think it's clear for you. I think till now you may get confused. You have to see the code, you have to run it your own, then only you can easily understand. So thank you guys. If you have any doubt means you can ask now. If you have any doubt means you can ask now. Can you suggest some good books? So there is a website called Accelera. So I will show you the. So you can also join our internship program. I will share the book directly, but for your reference, I will share the some. So you can see here Accelera. So Accelera is a standardized like a company. They are providing SystemVerilog books and then UVM books. You can use for the it is an IEEE center. So Accelera is a vendor. They are giving the books, and also you will get the LLM. So LLM, it's like a language. Just a minute. So they are giving also LLM. So LRM, language reference manual. So this is SystemVerilog basic book. If you need means you can go for the Accelera LRM. You will get the SystemVerilog book. You can learn. Okay, you can see there are a lot of 586 pages. You can learn yourself. Okay, so it is very clear, and also there are a lot of books in the market. You can buy freely. This SystemVerilog design. So there is my PPT, I think so. So I think choose the Accelera books. It is very simple and it's very useful for you. As long as you are showing the code, I am able to understand. But while writing my own many years old. So I think it may happen, but you have to do daily. So you have to debug your code, like you have to rectify your errors. It's a very good lesson for you because of without seeing the code, while seeing the code, it is very understandable for you. But while writing the code your own means, you may receive lot of confusions. You may receive like a errors, like a syntax error, how the syntax is happening, how the randomization will, how the randomize we can do, and then what is the syntax for this clocking block, what is syntax for the mailbox, what is syntax for enum. So you may receive lot of syntax errors and also assignment errors, and also while in the design code you may receive the metastability if you are using the flip-flop, if you are using the sequential logic. So on that time you have to use the double register. A lot of things you have to learn. So by rectifying your errors, you can good in code writing. Okay, coding skill. So just do practice daily. You will get better results. Okay, so I think this is for today. So thank you for your response, Naveen Rathe, thank you for your valuable feedback. It's very pleasure for me. So and then Vijay Kumar, thank you. Something while adding sensor clock errors. So while interfacing sensor with FEJ, you were asking like FEJ means you have to make your protocol very correctly. So if you are using like a GSM or else any sensor using the I2C protocol, so you can use for example, assume like you have the FEJ board, and then you having the slave device like a LCD module. It is used the I2C protocol. So in the LCD module, it already having the I2C module. So in the LCD module, it having the I2C chip. It is act like a slave device. There is an address. Every I2C LCD module, it having some address like a 3F, 2F, 27 kind of thing it having. So while writing the code, you are writing the master code in the Verilog. So for the slave address you have to give the correct slave address, and also you have to make the clock frequencies. The LCD module work with some different clock frequency. Here also your FPGA work with the different clock frequency. Assume like your FPGA having the 50 megahertz, in the I2C it having the 8 megahertz. So you have to make synchronization between them. So that's why I'm telling, practicing it's very good for you. So if you receive any error means, you can there are a lot of there are a lot of solutions for you. There is an community in VLSI community in LinkedIn. Also you can post your error in our pantechelearning LinkedIn page, and then we can try to resolve that. And also there are a lot of resources in the internet you can use for your error messages. Okay, so thank you guys, thank you for listening. We'll see tomorrow. Thank you for response. So we'll see tomorrow with the new protocol like AHP, high speed protocol. So I think it's clear for you. Thank you guys, thank you for listening. Good night.